So lesson 4.5 doesn't exist in your book. Every once in a while, the College Board will add things to AP curriculum. And so over the summer, they added this concept to what was required for an AP class. But our book doesn't have it. And so rather than spend the money to get a whole new book, I just wrote a new lesson. So I call it 4.5 because it's what should fit into chapter 4, but it doesn't exist in your book. If you're looking for section 4.5, you want to read about 4.5, you're not going to find it. Okay, so I just did some external research and kind of looked up and made up some examples to help us be able to do this new thing where they're going to ask you to understand what the derivative of an inverse function is. It's different than the inverse trig function. Those have always been part of the curriculum. And you learned those already, those 1 over the square root. Okay, but an inverse function itself, this is new. Okay, so we need to go back and review what an inverse is. So let's start there. All right, so let's start with what is an inverse? That's the question. All right, if a function, f of x, passes both tests, if it passes the test to be a function, which is the VLT, okay, the vertical line test, and it also passes the additional test of being the horizontal line test, then we say that f of x is called a one-to-one function. And what that means is every 1x is uniquely paired with 1y and vice versa, and every 1y is uniquely paired with 1x. If you're just a VLT, you can have a y paired with multiple x's. But if you're an inverse, a one-to-one function, then it goes both ways. A single x is only ever paired with a single y, and a single y is only ever paired with a single x. That's what's called a one-to-one function. If it's a one-to-one function, so then comma, and the inverse exists. And the inverse notation is f negative 1 of x. Now, everything is switched between a function and its inverse. All the x values are switched with all the y values. All the y values are switched with all the x values. All the domain of one becomes the range of the other, and the range of one becomes the domain of the other. Everything is flip-flopped between a function and its inverse. All right, so we say if a is on the function f of x, then a must be paired with something. Okay, and it's only paired with one thing. So if a is on f of x, then f of a is paired with b. And that's a single relationship that would only be true in a one-to-one function. Then if b is on f inverse of x, then f inverse of b is paired with what value? Hey, exactly. That's completely how inverses work. Okay, if you plug 1 into the original function and you get 5, well then if you plug 5 into the inverse function, you will get 1. Okay, that's how inverses are designed. Okay, so we have to have that little concept of what an inverse is and what the definition of pairing things are in order to develop the derivative. Okay, okay, there we go. All right, so here we go. We're going to develop the derivative together. When you develop a derivative, you've got to start with something that's true. We're going to start with the following. G is equal to f inverse. We're going to start with that. So it's like you're given in geometry. Okay, I'm giving you this, and this is true. We're going to say G is the inverse of F. Now, as long as we do legal math to both sides, that's part of a math proof. Okay, it's different than a geometry proof. It's just making sure you do legal things to both sides. So one thing that's legal is just to make sure sometimes we add to both sides, or sometimes we square root both sides, or whatever you do it to the same side. Okay, so I am going to apply f to both sides. I'm going to take f and I'm going to compose it with g, but if I do it on that side, I also have to do it on the other side. So I'm going to take f and compose it with f inverse. Does anything happen when I do that? Okay, the right side can simplify. F as a function, when it combines with f inverse, the two negate each other. It's like taking a step forward and taking a step back. You end up right back where you started again. Those two things, okay, that works with any inverse. If we could bind sine with arcsine, they would cancel each other out. If we take a square with a square root, they cancel each other out. If we take an e with a natural log, they cancel each other out because they are inverses of each other. And so we get down to it just is x, because those two, by definition, those two things cancel each other out. Now I'm going to do the derivative. Okay, so I'm going to take the derivative on both sides. Taking the derivative of x is easy. That's just 1. But how do I take the derivative of a composite function where f is on the outside and g is in the middle? Chain rule. Okay? And so the rule for the chain rule says start with the outside, but do what to the inside? Keep it, nothing. And then chain on the rest. So we're going to start with the outside, which is f prime. Leave the inside alone. Tack onto that the next derivative, which would be g prime, and leave that alone. Just barely ran out of room. And then tack onto that the derivative of the inside, which is x, which is 1 again. Okay. We would like to get this part by itself. So what do I do to both sides? So all I want to do is get that yellow square by itself. I just divide, for sure. Okay, so g prime of x is 1 over f prime of g of x. And what was g originally? G was the inverse. And so if I've now found the derivative of g, I have now found the derivative of the inverse. Now we want to stop and pause and plug in a particular value. Okay? So I want you to recall that g of b, if g is the inverse, what should I end up with? What is g of b paired with? A. So then what would g prime of b be? What would it work out if I plugged b into the derivative? So let's try g prime of b. Well, that would be 1 over f prime of g of b. And what did I just get done saying that g of b was? A. So that turns into 1 over f prime of a. So to summarize, g prime of b is 1 over f prime of a. G prime is the derivative of the inverse. F is the original function. And so we say the derivative of the inverse is the reciprocal of the derivative of the original. but you got to plug in the opposite number. Okay, this is the one weird thing about inverse derivatives. If you're finding the derivative at a particular number, you don't actually plug that number in. You plug in what it's paired with because you're working with an inverse. Do you see that? It's not just g prime of b is 1 over f prime of b. The b is not what gets plugged in. It's the a that gets plugged in. That's where, like on a multiple choice problem, notice those two things, they don't match up. They're paired together, but it's not a direct correlation. And so on a multiple choice, they will catch the people who plug in the actual value of b. So this is, right here, what I just ended with. This is the inverse rule for derivatives. The derivative of the inverse is the reciprocal of the derivative of the original. Sometimes it helps us say it in words. The derivative of the inverse is the reciprocal of the derivative of the original, plugging in the paired value rather than the same value. So let's try a couple problems and see how it works when you're actually working with a real thing. F of x equals 7x cubed plus the natural log of x quantity cubed. You're given that. You're also given f of 1 turns out to be equal to 7, which you could figure that out. You could plug 1 into that and work it out to 7. Your job is to find g prime of what number do you think? G prime is going to be of 7, not of 1. So the definition of g prime of 7 is the reciprocal of f prime of what number? 1. The value of g prime of 7 is the reciprocal of 1 over f prime of 1. Not of 7 again, but of what 7 is paired with. And so now I just have to do 1 over, and I have to find the derivative of 7x cubed plus the natural log of x quantity cubed, and I have to find the derivative of that. So the derivative of 7x cubed is 21x squared plus the derivative of 3 natural log x is 3 quantity ln of x quantity squared. So what am I missing? I need the chain rule, which is 1 over x times 1. That is what I'm going to plug 1 into, and it will simplify very nicely for me. So I'll have 1 over 21 plus 3 times the ln of 1 quantity squared times 1. What's the natural log of 1? The natural log of 1 is right where the natural log function crosses the x-axis. Okay, the natural log of 1 is 0, and so we get 1 over 21, and that's the value of the derivative. So the value of the derivative tells you what the slope would be on the inverse function at that position. Okay, think of it in terms of slope. So the slope on the derivative is the reciprocal of the slope on the original. The slope on the inverse, I think I said it wrong. The slope on the inverse is the reciprocal of the slope on the original. Not perpendicular, because perpendicular would be reciprocal and change the sign. Okay, on an inverse, the slope on an inverse is just equal to the reciprocal of the slope on the original. So this really doesn't get much simpler than that if you think about it in terms of slope. So let's try another one. Bless you. All right, given the function f of x equals 3x to the 5th plus 6x to the 3rd plus 4, find g prime of 13. So I didn't give you very much to work with here. Okay, so by definition, g prime of 13 is 1 over f prime of something else. So I didn't give you a whole lot to work with here. I have to work a little bit backwards. G prime of 13 is 1 over f prime of something else. How do I find that number? Okay, no, that's what they want you to do. Okay? They want you to plug 13 in for x, but that's not right. Okay, it's okay. It's all right. We want to know what do we actually plug in for x to make it be 13. So you're going to have to do a little work over here. Okay, 3x to the 5th plus 6x to the 3rd plus 4 equals 13. And these are not going to be super complex questions. It's usually kind of an obvious number that would work out to have that to work out. I mean, look at 3 and 6 and 4 are your coefficients, right? So if you've got 3 and 6 are 9 and then 4, so what do you think x is going to be? 1. X is 1. And so we are actually going to be plugging in 1. So that's a little bit of the work we have to do, is to figure out what that value is that's paired with 13. 1 and 13 go together in this inverse thing. And so now I need to find the derivative. So the derivative of 3x to the 5th is 15x to the 4th. The derivative of 6x cubed is 18x squared. And then the derivative of 4 is 0. If I plug 1 into that, I'll have 1 over 15 plus 18. So 1 over 33. If the slope on the inverse at 13 was 1 over 33, what was the slope on the original function? 33. Where? At x equals 1. Okay, very good. Okay, let's try one more. All right, find a tangent line to the inverse of f of x equals x to the 5th plus 2x to the 3rd plus x minus 4 at negative 4, 0. Find a tangent line to the inverse of that at negative 4, 0. All right, so what two things do you need for your tangent line? Okay, slope and a point, right? We have our point. Our point is given at negative 4, 0. Negative 4, 0 is on which of the two functions? The original or the inverse, the way it's written? Check it. If you plug negative 4 in, are you going to get 0? Okay? No, if you plug 0 in, you're going to get negative 4. So negative 4, 0 is on the inverse. Which means 0, negative 4 is on the original. Our slope. We would like to find g prime of negative 4, which means I will be finding 1 over f prime of what number? 0. Okay, so 1 over. The derivative of the function we've been given is 5x to the 4th plus 6x to the 2nd plus 1. So if I plug 0 into that, I simply get 1. So my tangent line will be using the given point and the given slope. So y equals x plus 4 is the tangent line. It's not the tangent line to the original function, it's the tangent line to the inverse of the original function. I want you to notice one thing in common with all of these problems. Did we ever actually find the inverse? We never actually found the inverse. You can find the derivative without having to find the inverse. Okay? Finding the inverse is a Herculean task. Okay? It's this massive effort. To find the inverse of this function, you'd have to switch all the x's and y's and then try and solve and get y alone by again. Okay, that's horrible when you have a polynomial combined with a natural log. Even the same thing with this. To find the inverse of a quintic, you'd need the quintic formula, which is a version of the quadratic formula, but it's way more complex. All right, and so the whole point of calculus is that you can find the value of the derivative of the inverse without actually finding the inverse itself. It's only based on the reciprocal of the derivative of the original function. So if you can find the derivative of the original, you're fine. You don't have to actually find the inverse in order to be able to do that. Okay, so that was a new lesson added to the AP curriculum for you guys this year. So there is a worksheet that I made that is your homework. Okay, it's not in the book. So what I'd like you to do is, if you would like to print the worksheet, that's fine. If you want to just do it right on your iPad and submit it through Canvas that way, that's fine. If you wanted to copy the problems onto notebook paper and do it that way, that's fine, whatever your preference is for how you do that worksheet for 4-5, okay? But you won't need your book.